What if I told you that the most important thing about our universe is something no one can actually point to? Right now, as you sit here, the universe is expanding. Every second, galaxies are drifting farther apart. Space itself is stretching. This isn't theory anymore. It's measured, proven. But here's the strange part. If everything is moving away from everything else, then a simple question should have a simple answer. What is it expanding into? More space? A giant empty void? Some kind of cosmic container? It sounds obvious that there must be something outside. But physics gives a very uncomfortable answer. There is no outside. And that's where things stop making sense. Because in our everyday life, everything expands into something. A balloon expands into the air. A fire expands into a room. Even an explosion needs space to spread. So how can the universe expand if there's nowhere for it to go? This isn't just a philosophical puzzle. This is a real physical question that sits at the edge of modern cosmology. And the deeper scientists look, the stranger the answer becomes. Because it turns out, the universe isn't expanding into anything. Instead, space itself is being created. Every second, everywhere. To understand this, we need to drop one very natural assumption. We instinctively imagine the universe like an object, something sitting inside a bigger space. But that picture is wrong. The universe is not in space. The universe is space. There is no background, no container, no outer wall. When we say the universe is expanding, we don't mean galaxies are flying outward into emptiness. We mean the distance between everything is increasing. Imagine dots drawn in the surface of a balloon. As the balloon inflates, the dots move away from each other. Now ask yourself, where is the surface expanding into? From the perspective of those dots, there is no outside. They only experience the surface itself. In the same way, we are like those dots, except instead of a 2D surface, we live in a 3D space that is expanding in a way we cannot step outside of. So when we ask, into what? We're secretly assuming something that may not exist at all. An outside. This idea didn't come from imagination, it came from observation. In the 1920s, an astronomer named Edwin Hubble made a discovery that changed everything. He observed distant galaxies and noticed something shocking. The farther away a galaxy is, the faster it is moving away from us. Not randomly, not in different directions, but in a smooth, predictable pattern. This became known as Hubble's law, and it revealed a profound truth. The universe is not static. It is expanding uniformly in all directions. But here's the key detail. It's not that we're at the center of expansion. Every point in the universe sees the same thing. No matter where you are, it looks like everything else is moving away from you, which means there is no center. And if there is no center, there is no edge. At this point, things begin to stretch the limits of intuition, because we're forced to accept something deeply unfamiliar. The universe can be finite and still have no boundary. This sounds impossible, but think of the surface of the Earth. If you walk in a straight line long enough, you'll eventually come back to where you started. There is no edge to fall off. Yet the surface is not infinite. In a similar way, the universe might be curved in higher dimensions. Not curved into something we can see, but curved in a way that is built into the structure of space itself. This idea comes from Albert Einstein and his theory of general relativity. According to this theory, space is not just an empty stage. It is dynamic, flexible. It can stretch, bend, and evolve. So when we ask, what is the universe expanding into? Einstein's equations quietly respond, that question may not apply. Because expansion doesn't require an outside. It only requires that the geometry of space itself is changing. If space itself is expanding, then we need a way to measure that expansion. Not with rulers or meters, but with something much more fundamental: light. When observers distant galaxies, they don't just look at where they are, they study the light coming from them. And something very strange happens to that light. It gets stretched. This effect is called redshift. As space expands, the wavelength of light traveling through it also expands. Blue light shifts towards red. Red shifts even further into infrared. This isn't because galaxies are simply moving through space. It's because the space between us and them is stretching while the light travels. This distinction is critical. In everyday motion, objects move through space. But here, space itself is changing, and light is being carried along with it. The deeper explanation comes from solutions to Einstein's equations known as the Friedmann equations, developed by Alexander Friedmann. These equations describe how the scale factor of the universe evolves over time. The scale factor is essentially a number that tells us how big is the universe compared to before. And according to these equations, that number is increasing. Now here's where things become even more unsettling. You might think, if the universe is expanding, then maybe it started from a single point and is growing outward. That sounds reasonable, but it's not quite right. The event we call the Big Bang was not an explosion in space. It was an expansion of space. There was no center, no location where it happened. Every point in the universe was once compressed into an extremely dense, hot state, and then everything expanded simultaneously. This means something deeply counterintuitive. The Big Bang happened everywhere. Not at a point you could travel to, not somewhere far away, but right where you are sitting, right now. The space you occupy today was once part of that initial state, but if expansion has been happening since the beginning, what is driving it? Why doesn't gravity pull everything back together? For a long time, scientists believed expansion should be slowing down. After all, gravity attracts matter. Galaxies should gradually decelerate as they pull on each other. But in 1998, two independent teams studying distant supernovae made a discovery that shocked the entire field. The expansion of the universe is not slowing down, it's speeding up. Something is pushing space to expand faster and faster. This unknown force was given a name: dark energy. We don't know what it is. We don't know where it comes from, but we can measure its effect. Today, dark energy makes up about 68% of the total energy content of the universe, and it behaves in a very unusual way. Instead of pulling things together like gravity, it pushes space apart. On the largest scales, it dominates everything. To understand how strange this is, we need to look at a concept from physics called the cosmological constant. This idea was first introduced by Albert Einstein. He added it to his equations as a way to keep the universe static. Later, he abandoned it when expansion was discovered, but now it has returned in a completely different role. The cosmological constant can be thought of as the energy of empty space itself. Even when you remove all matter, all radiation, everything, space is not truly empty. It has a built-in energy. And as the universe expands, more space appears, which means more of this energy appears. And that leads to a bizarre conclusion. The total energy of the universe might actually be increasing over time. Not because energy is being created in the usual sense, but because the fabric of space itself carries energy. At this level, we are no longer dealing with everyday intuition. We are dealing with the structure of reality itself. In modern cosmology, expansion is described using something called metric expansion. This means the distances between points are increasing because the underlying geometry of space is evolving, not because objects are moving in the usual sense. Think of it like this. If you draw a grid on a rubber sheet and stretch the sheet, the grid lines move apart. But no point is moving across the surface. The distances themselves are changing. That's what's happening in the universe. Galaxies are mostly sitting still relative to their local space, but the space between galaxy clusters is expanding. And the farther away something is, the faster it appears to recede. Not because it's moving fast, but because there is more expanding space between you and it. Now we reach a deeper and more unsettling realization. If expansion continues forever, there will come a time when distant galaxies move away from us faster than light. This does not break the laws of physics, because nothing is traveling through space faster than light. Instead, space itself is expanding, and general relativity allows this. Eventually, those galaxies will cross a boundary known as the cosmic horizon. Beyond that point, their light will never reach us. Not now, not ever. They will effectively disappear from our observable universe. This leads to a haunting possibility. In the far future, observers in our galaxy may look out into space and see almost nothing. No distant galaxies, no evidence of expansion, no trace of the Big Bang. Just darkness. According to quantum physics, empty space is not truly empty. It behaves more like a restless ocean. Even in a perfect vacuum, no particles, no radiation, there are still tiny fluctuations happening everywhere. Pairs of particles briefly appear and disappear. Energy flickers in and out of existence. This is not speculation. It comes directly from the mathematics of quantum field theory. In this framework, every type of particle is associated with a field that exists throughout all of space. And even when those fields are in their lowest possible energy state, they are never completely still. This is called the quantum vacuum, and it may be the key to understanding why the universe expands the way it does. Here's where things become both precise and deeply confusing. If empty space has energy, then that energy should act like a source of gravity. But instead of pulling things together, it does the opposite. It creates a kind of negative pressure. In Einstein's theory, gravity is not just caused by mass or energy, it is influenced by pressure as well. And negative pressure has a very strange effect. It makes space expand faster. This is exactly the behavior we observe with dark energy. So one leading idea is this: dark energy might simply be the energy of the quantum vacuum. But when physicists try to calculate how much energy should be there, they run into one of the biggest problems in all of physics. The predicted value of vacuum energy is wildly wrong. Not a little wrong, not even close. Off by a factor of about 10 to the 120th. This is known as the cosmological constant problem. It is often called the worst theoretical prediction in physics. Quantum theory suggests that empty space should contain an enormous amount of energy. If that were true, the universe would expand so violently that galaxies could never form. Stars, planets, and life would not exist. But that's not what we see. Instead, the expansion is slow and controlled, just enough to shape the large-scale structure of the universe. So something is missing from our understanding. Either our calculations are incomplete, or there is some unknown mechanism canceling out most of that energy. Now let's return to the original question. If the universe is expanding, but not into anything, what does that really mean at the deepest level? It means that space is not a passive background. It is an active, evolving system. Its geometry can change. Its energy can influence motion. Its structure may even emerge from something more fundamental. Some physicists believe that space itself is not fundamental at all. Instead, it could be built from deeper, microscopic ingredients, something like atoms of space.
In certain approaches to quantum gravity, space is described as a network of connections, not continuous but made of discrete units. And what we perceive as expansion could be the result of this network growing or rearranging. This idea is still under development, but it suggests that asking "into what" might be like asking, what is a wave expanding into on the surface of water? The answer is not outside the system, it is within the structure itself. There is one more layer to this, and it challenges the very idea of nothing. We often imagine that outside the universe there is nothing. But physics struggles with that concept because nothing is not easy to define. Is it the absence of matter? The absence of space? The absence of laws? In modern physics, even a vacuum has properties. It has energy. It has structure. It follows laws. So true nothingness may not exist in any physical sense, which means the question, what is outside the universe, may not have an answer because there may be no such thing as outside. And yet, the mystery remains, because while our equations describe how the universe expands, they don't fully explain why this universe exists at all. Why these laws? Why this energy? Why this structure of space and time? Some theories attempt to go further. Ideas like the multiverse suggest that our universe may be one of many, each with different properties. In that picture, expansion could be just a local feature of a much larger reality. But as of now, these ideas remain speculative. We have no direct evidence, only mathematical hints. Up to this point, we've treated expansion as something smooth and predictable. But there's an important detail hidden in the equations. The rate of expansion is not constant over time. It evolves. This evolution is described as solutions to Einstein's field equations, often written in terms of the scale factor and how it changes with time. Depending on what the universe contains, matter, radiation, dark energy, the expansion behaves differently. In the early universe, matter dominated. Gravity was strong enough to slow the expansion down. Later, as the universe expanded and matter became more diluted, something else began to take over: dark energy. And once dark energy dominates, something remarkable happens. Expansion doesn't just continue, it accelerates exponentially. This means that over time, distances don't just increase steadily, they grow faster and faster in a runaway process. This accelerated expansion leads to a very specific prediction. Over extremely long timescales, structures in the universe become isolated. First, distant galaxies disappear beyond the cosmic horizon. Then galaxy clusters break apart in terms of causal contact. Eventually, even neighboring galaxies become unreachable. Our local group of galaxies, bound together by gravity, will remain intact, but everything beyond it will fade away. Not because it vanishes, but because the space between us and it expands too quickly for light to ever reach us again. This creates what physicists call a de Sitter universe, named after Willem de Sitter. In such a universe, space expands exponentially due to a constant energy density. And it has a strange property. It contains its own kind of horizon, a boundary beyond which events can never influence you. This horizon is not like a wall. It's not something you can touch or see directly. It's a limit defined by the speed of light and the expansion of space. And it creates a profound consequence. There are regions of the universe that are permanently disconnected from us. No signal, no particle, no information can ever cross that boundary toward us. In a sense, parts of reality exist, but are forever inaccessible. This is not due to technology, not due to distance alone, but to the fundamental structure of space-time. Now, let's take this one step further. If expansion continues accelerating, the universe approaches a state often called heat death. Not an explosion, not a dramatic collapse, but a gradual fading. Stars burn out. Galaxies grow dark. Black holes slowly evaporate over unimaginable timescales through a process predicted by Stephen Hawking. Energy becomes evenly spread out. No gradients, no differences. And without differences, no work can be done. No structure can form. Physics continues to operate, but nothing interesting happens anymore. However, there's another, more extreme possibility. It depends on the exact nature of dark energy. So far, we've assumed that dark energy has a constant density. But what if it changes over time? If dark energy becomes stronger, the expansion could become so intense that it begins to tear apart structures, not just galaxies, not just solar systems, but eventually atoms themselves. This scenario is known as the Big Rip. In this case, the expansion rate increases without limit. At some point, even the forces holding matter together cannot resist it. Space expands so violently that everything is pulled apart, from galaxy clusters to stars to planets to molecules to atoms. On the other hand, there is also the possibility, though current evidence makes it unlikely, that expansion could reverse. If the total energy density of the universe were high enough, gravity could eventually overcome expansion. The universe would stop expanding and begin to contract. This leads to a scenario known as the Big Crunch. In this picture, everything collapses back into a hot, dense state, possibly similar to the beginning. Some theories suggest that this could even lead to a new expansion phase, a cyclic universe, expansion followed by contraction, again and again. But current observations of dark energy suggest that our universe is not heading in that direction. At this stage, we are dealing with possibilities that extend far beyond direct observation. So how do we test any of this? The answer lies in precise measurements of the universe today. By observing distant supernovae, the large-scale distribution of galaxies, the cosmic microwave background, scientists can infer how expansion has behaved over time. One of the most important pieces of evidence comes from the cosmic microwave background. This is the afterglow of the early universe, a faint radiation filling all of space. It provides a snapshot of the universe when it was only about 380,000 years old. Tiny fluctuations in this radiation tell us about the geometry of space, and those measurements indicate something remarkable. On large scales, the universe appears to be very close to spatially flat. A flat universe has a very specific implication. It means that parallel lines remain parallel. The geometry follows the familiar rules we learn in basic geometry. But here's the key point. Flat does not mean infinite. It only describes curvature. A flat universe can still be finite if it has a topology that loops back on itself, or it could be truly infinite. We don't yet know. And this brings us once again to the original question. If the universe is expanding but has no edge and no outside, then what are we really describing? We are describing a system where space is dynamic, geometry evolves, energy is built into the vacuum, and observation itself is limited by the structure of spacetime. So far, we've treated spacetime as the stage on which everything happens. Even if it bends and expands, it's still the background. But some of the most serious attempts to unify physics suggest something radical. Spacetime might not be fundamental at all. It might be emergent. In other words, space could be something that appears at large scales, but does not exist at the deepest level of reality. This idea comes from efforts to reconcile general relativity with quantum mechanics. Because when you try to apply quantum principles to space-time itself, the equations stop behaving well. They produce infinities, break down, lose predictive power. This suggests that we may be using the wrong description at very small scales. Just like temperature is not a fundamental property, it emerges from the motion of atoms, space and time might emerge from something deeper. One approach to this problem comes from what is known as loop quantum gravity. In this framework, space is not continuous. It is made of tiny, discrete units, almost like pixels, but far smaller than anything we can currently measure. These units are connected in a network-like structure, and geometry, distance, area, volume, arises from how these connections are arranged. So when we say the universe is expanding, it might not mean that a smooth fabric is stretching. It could mean that this underlying network is changing, new connections forming, existing ones rearranging. In this view, expansion is not happening within space. It is happening because space itself is being built moment by moment. Another powerful idea comes from a completely different direction. Instead of focusing on the structure of space, it focuses on information. In certain theories, the fundamental building blocks of reality are not particles or fields, but bits of information. This leads to the concept that space-time itself may emerge from patterns of information. One of the most influential ideas in this direction is the holographic principle. It suggests that the information describing a volume of space can be encoded on its boundary. This idea was inspired by the physics of black holes. When matter falls into a black hole, its information does not disappear. Instead, it is thought to be stored on the surface, the event horizon. This insight was developed further by physicists like Gerard 't Hooft and Leonard Susskind. If this principle applies to the entire universe, then what we experience as three-dimensional space could be a projection of information encoded on a lower dimensional boundary. This is not science fiction. In certain models, especially those studied in string theory, this idea works mathematically. A well-known example is the correspondence between gravitational theories in higher dimensional space and quantum field theories without gravity in lower dimensions. What this suggests is deeply unsettling. The space you experience might not be fundamental. It could be a kind of emergent description, like a shadow of deeper processes. And if space itself is emergent, then asking, what is it expanding into, becomes even more complicated, because the expansion may not be happening in any traditional sense at all. Now consider how this connects back to expansion. If space-time emerges from information or quantum structure, then expansion could reflect a change in that underlying information, not an outward motion, not growth into something else, but an increase in the number of fundamental degrees of freedom. In simpler terms, the universe might be gaining complexity at its most basic level, and what we perceive as expanding distances is just the large-scale effect of that deeper process. This shifts the question entirely. Instead of asking, what is the universe expanding into, we begin to ask, what is giving rise to space in the first place?
Not an outward motion, not growth into something else, but an increase in the number of fundamental degrees of freedom. In simpler terms, the universe might be gaining complexity at its most basic level, and what we perceive as expanding distances is just the large-scale effect of that deeper process. This shifts the question entirely. Instead of asking, what is the universe expanding into, we begin to ask, what is giving rise to space in the first place? There's also a deep connection between expansion and entropy. Entropy is a measure of disorder, or the number of possible configurations of a system. The second law of thermodynamics tells us that entropy tends to increase over time, and the universe follows this rule. As it expands, entropy increases. Structures form, evolve, and eventually decay. But here's the key insight. Some physicists believe that the expansion of the universe itself may be driven by the growth of entropy. In this view, the direction of time, the expansion of space, and the increase of entropy are all linked, not separate processes, but different aspects of the same underlying principle. This leads to a profound possibility. What we perceive as time flowing forward may be tied to the expansion of the universe. If the universe were not expanding, if entropy were not increasing, time as we experience it might not exist in the same way. This idea connects cosmology to the deepest questions about time itself. Why does time move forward? Why do we remember the past but not the future? One possible answer is that the expansion of the universe creates the conditions for this asymmetry. Now let's go even further. Some approaches suggest that space-time emerges from quantum entanglement. Entanglement is a phenomenon where particles become correlated in such a way that their states cannot be described independently, even when separated by vast distances. In recent years, physicists have found hints that the geometry of space-time may be related to patterns of entanglement. In certain models, changing the entanglement structure changes the geometry of space. Distances can shrink or expand depending on how systems are entangled. This suggests something extraordinary. Space itself might be a manifestation of quantum relationships, not a container, but a network of connections. If that's true, then expansion could be understood as a change in entanglement. As the universe evolves, the pattern of quantum connections changes, and what we interpret as increasing distance could be the result of those connections becoming less tightly correlated. In this picture, there is no need for an outside. There is only the internal structure of relationships, and expansion is a reconfiguration of that structure. At this level, the original question begins to dissolve, not because it has been answered in a simple way, but because the assumptions behind it no longer hold. The idea of into what depends on space being embedded in something larger. But if space itself is emergent, if it arises from deeper physics, then there may be no larger arena at all, no external space, no boundary, no outside. Only the system itself and the rules that govern how it evolves. To get there, we need to revisit the very early universe, not just the Big Bang, but what may have happened immediately after it began. There's a theory called cosmic inflation. It proposes that in the first tiny fraction of a second, the universe didn't just expand, it expanded extremely fast, faster than anything we see today, in an almost explosive burst. This idea was developed by physicists like Alan Guth to explain several puzzles in cosmology. For example, why is the universe so uniform in all directions? Why is space so close to flat? Inflation provides a solution. It stretches space so rapidly that any initial irregularities get smoothed out. But inflation introduces a new and unexpected possibility. It might not have happened just once. In some models, inflation doesn't completely stop everywhere. Instead, it continues in different regions of space. This leads to a concept known as eternal inflation. In this picture, parts of space keep expanding rapidly forever, but occasionally small regions slow down and form universes like ours. These regions are sometimes called bubble universes. Each bubble becomes its own universe with its own properties, its own expansion, its own physical conditions. Now, this sounds like it brings back the idea of an outside. If our universe is a bubble, then what is it inside of? In these models, the answer is subtle. The outside is not empty space as we imagine it. It is a rapidly expanding background, often called the inflationary field. This background is not something we can travel through because it expands so fast that any attempt to move through it would be overwhelmed by its expansion. So even if there is a larger structure beyond our universe, it is not accessible, not in principle, not even with infinite time. Each bubble universe forms when inflation locally ends. Inside that bubble, space behaves like our universe. Expansion slows to a rate governed by matter, radiation, and dark energy. But outside the bubble, inflation continues, separating bubbles from each other at enormous speeds. This creates a kind of cosmic landscape, a vast structure where new universes are constantly forming, but none of them can interact. Each is causally isolated. If this picture is correct, then our universe may not be unique. There could be countless other universes, each with different properties, different physical constants, different laws. Some may expand faster, some slower. Some may collapse quickly. Others may never form structure at all. And in that context, the question, what is our universe expanding into, changes again. Because now expansion is happening within our bubble, while the larger structure is doing something even more extreme. But there's a crucial limitation. We have no direct evidence of other universes. All observations we can make are confined to our observable region. Even signals from the earliest moments we can detect, like the cosmic microwave background, only tell us about our own bubble. There have been attempts to look for signs of collisions between bubble universes, patterns in radiation that might suggest interaction. So far, nothing conclusive. So while eternal inflation is mathematically consistent, it remains unconfirmed. Now let's push even further. There are theories suggesting that our universe might exist in more than 3 spatial dimensions. In some models, space has additional dimensions that are hidden or compactified. In others, our entire universe could be a brain floating in a higher dimensional space. These ideas come from string theory and related frameworks. In that context, expansion could be happening within our 3-dimensional slice, while a higher dimensional structure exists beyond it. But again, this beyond is not something we can directly observe, because all known forces, except gravity, may be confined to our 3-dimensional space. If extra dimensions exist, they might influence expansion in subtle ways. For example, gravity could leak into higher dimensions, or the geometry of those dimensions could affect how our universe evolves. But detecting this is extremely difficult. It requires either observing deviations in gravitational behavior or probing energy scales far beyond current experiments. So for now, these ideas remain theoretical. Every time we try to find an outside, physics reshapes the question. First, we learned that space itself is expanding, then that space may be curved and without edges, then that it may emerge from deeper quantum structures. And now, even when we introduce larger frameworks like inflation or extra dimensions, they do not give us a simple intuitive outside. They give us something far more abstract. So the original question, what is the universe expanding into, has transformed completely. It's no longer just about space. At this level, some physicists take a step back and ask a different kind of question. What if the universe is not just described by mathematics, but is mathematics? This idea is most strongly associated with Max Tegmark. According to this view, the universe doesn't exist within a mathematical framework. It is a mathematical structure. Every physical law, every constant, every interaction is simply part of that structure. And what we experience as space, time, and expansion are features of that mathematical system. In this picture, asking, what is the universe expanding into, is like asking, what is the number 5 expanding into? The question doesn't apply, because the system is self-contained. Now consider what this means for space itself. If reality is fundamentally mathematical, then space might not be a physical substance at all. It could be a way of organizing relationships within that structure. Distances, directions, and geometry would not exist independently. They would emerge from the relationships between elements. So expansion would not be a physical stretching. It would be a transformation of those relationships, a change in how the structure is arranged. There's another direction physicists explore, one that focuses on laws themselves. We often assume that the laws of physics are fixed, unchanging, timeless. But some theories suggest that even the laws might evolve. In such frameworks, the behavior of the universe could change over time. Constants might not be constant. Rules might not be permanent. If that's the case, then expansion might not just be a consequence of fixed laws. It could be part of a larger process where the rules themselves develop. This idea is highly speculative, but it addresses a deep question. Why do the laws of physics have the form they do? Now return to the concept of nothing. Earlier, we saw that physics struggles to define true nothingness. Even empty space has energy. Even a vacuum has structure. So what would it mean for there to be nothing at all? No space, no time, no laws. Some approaches suggest that such a state may be unstable, that nothing naturally gives rise to something, not through a process in time, but as a fundamental property of reality. In this sense, the existence of the universe might not require a cause in the usual way. It could be that something is the only stable possibility. This connects to ideas about quantum creation of the universe. In certain models, the universe can arise as a quantum event, not in space, but as the origin of space itself. These models use the mathematics of quantum mechanics applied to the entire universe, and they suggest that the universe could emerge from a state with no classical spacetime. Again, this does not mean nothing in the everyday sense. It means a state beyond our usual categories, a state where the distinction between something and nothing may not even apply. At this depth, the original question has transformed completely. What is the universe expanding into becomes inseparable from deeper questions. What is space? What is time? What is existence? Because expansion is not just a motion, it is a feature of how reality itself is structured. And if that structure is emergent, relational, or mathematical, then expansion is not happening into anything. It is happening as part of the system's internal evolution. And yet, even with all of this, there is something remarkable. Despite the layers of abstraction, the equations work. They predict observations with extraordinary accuracy. From the motion of galaxies, to the afterglow of the early universe, to the acceleration of expansion, the mathematical descriptions align with reality. This suggests that even if our intuition fails, the underlying structure is consistent, coherent, describable. So where does this leave us? We started with a simple question, a natural question, the kind of question anyone might ask. What is the universe expanding into? And we followed that question through multiple layers, from galaxies to space-time, to quantum fields, to information, to possible multiverses, to the nature of existence itself. At each step, the answer did not become simpler. It became deeper and more abstract. At this point, a different kind of question begins to emerge. Not what is the universe expanding into, but can we ever truly know the answer? Because every explanation we've explored depends on observation, data, light, signals, and all of those are limited. There is a boundary to what we can see, known as the observable universe. It's not the edge of reality, it's the edge of what information has had time to reach us. Light travels at a finite speed, so when we look far away, we are looking back in time. The farther we look, the earlier we see. But beyond a certain distance, light has simply not had enough time to arrive. This creates a fundamental limitation. There may be regions of the universe, or even entirely different structures, that are forever beyond our reach. Not because they are hidden, not because we lack technology, but because of the way space-time itself is structured. Even if we waited forever, signals from those regions would never arrive. This is not a practical limit. It is a principled limit, built into the laws of physics. Now combine this with accelerated expansion. As we saw earlier, distant galaxies are moving away faster and faster. Over time, more and more of the universe slips beyond our observable horizon. Information that is visible today will become unobservable in the future. In other words, the universe is not just expanding. Our access to it is shrinking. Future observers may know less about the universe than we do now because the evidence will no longer be visible. This leads to a striking possibility. Cosmology itself may have a limited window, a period in the history of the universe when it is possible to discover its large-scale structure. We happen to live within that window, early enough that we can still see distant galaxies, late enough that complex structures and observers exist. But this window will not last forever. Now take this idea even further. If there are limits to observation, there may also be limits to theory. Physics relies on testing ideas against evidence, but if certain aspects of reality are permanently unobservable, then no experiment can confirm or deny them. This raises a deep question. Is it possible that some truths about the universe are fundamentally beyond science? Not because they are mystical, but because they are inaccessible. This is not just philosophical. It affects real scientific debates. For example, in theories involving multiple universes, we may never be able to observe other universes directly. We can build models, we can explore mathematical consistency, but without observable evidence, confirmation becomes difficult. This challenges the traditional boundary of physics. Where does science end and speculation begin? And yet, even within these limits, something remarkable remains. The part of the universe we can observe is governed by consistent laws. Patterns repeat. Structures follow rules. Mathematics describes behavior with extraordinary precision. This suggests that even if we cannot access everything, what we can access is not random. It is ordered, structured, understandable, at least in part. Now return one last time to the original intuition. The feeling that the universe must be expanding into something, that there must be an outside, that there must be a larger space beyond. That intuition comes from everyday experience, from living inside environments with boundaries, rooms, containers, surfaces. But the universe is not an object inside a larger room. It is the entire system, all space, all structure, all that we can physically describe. And that may be the deepest shift required to understand this question, not adding more layers, but letting go of certain assumptions. The assumption that everything must have an edge. The assumption that expansion requires an external space. The assumption that reality behaves like familiar objects. Because at the scale of the universe, those assumptions no longer hold. So instead of imagining the universe expanding outward, we begin to see it differently, as a system whose internal relationships are evolving, distances increasing, geometry changing, information rearranging, not moving into something else, but transforming from within. And in that sense, the question, into what, reveals something important, not about the universe itself, but about how we think. It shows the limits of intuition, the ways in which everyday reasoning breaks down when applied to cosmic scales, and how physics, step by step, replaces intuition with deeper, more abstract understanding. At the deepest level, physicists are searching for something often called a final theory, a single unified framework that explains gravity, quantum mechanics, space-time, energy, and the origin of the universe, all in one consistent structure. Right now, we have two incredibly successful theories: general relativity, which describes gravity in the large-scale universe, quantum mechanics, which describes the smallest scales. Both work very well, but they don't fully agree with each other. When we try to combine them, especially in extreme conditions like the Big Bang or inside black holes, the mathematics breaks down. A final theory would resolve this. It would tell us what space-time really is, whether it is continuous or discrete, whether it is fundamental or emergent, and possibly what expansion truly means at the deepest level. But even if we discover such a theory, there is a deeper question. Will it answer everything? Or will it simply move the mystery one step further? Because even a perfect set of equations raises another question. Why those equations? Why that structure? Why does reality follow any rules at all? A final theory might describe how the universe works, but not necessarily why it exists. This leads to an idea that some physicists and philosophers consider. Perhaps not all questions have answers, not because we are limited, but because reality itself may not contain those answers. There may be boundaries to explanation, points beyond which asking why no longer leads to deeper understanding, but simply reaches the limits of the system. Another direction explores whether the universe is fundamentally computable. That is, whether everything that happens can be described as a kind of computation. In this view, the universe operates like an information processing system. Every interaction, every event, every change follows rules similar to an algorithm. If this is true, then expansion itself could be part of that computation, a process unfolding step by step, state by state. But even here, limits appear. There are results in mathematics and computer science suggesting that not everything can be computed. Some problems cannot be solved by any algorithm. Some truths cannot be proven within a given system. If the universe shares these properties, then there may be aspects of reality that are fundamentally beyond calculation. Not just difficult, but impossible to fully determine. So now we arrive at a profound crossroads. We have theories that describe expansion with precision, models that explain how space evolves, ideas suggesting space itself may emerge from deeper structures. And yet, when we ask the simplest version of the question, what is the universe expanding into? We find that the question itself begins to dissolve, because the answer is not a place, not a region, not a larger container. Instead, the answer lies in understanding that the universe is not expanding into anything. It is expanding as part of its own structure. Space is not inside something else. Space is the system, and its expansion is a change in that system, not movement within a larger one. What began as a simple curiosity, something that feels obvious at first, leads us through layers of understanding, from galaxies moving apart, to space-time stretching, to quantum fluctuations in empty space, to information and entropy, to the possibility that space itself is not fundamental. And at each step, the idea of an outside becomes less meaningful. So in the end, the universe does not expand into anything we can point to. There is no edge to cross, no boundary to reach, no outer space beyond space itself. Instead, the universe expands because its own geometry evolves, because its structure changes, because the rules that define it allow that change to happen. And the deeper we go, the clearer it becomes. The question was never just about the universe, it was about how we understand reality. And sometimes, the most important discoveries in physics are not the answers we find, but the questions we learn to ask differently.